It's a great pleasure to have Rusa Mandal here as part of our IMSc 60 colloquium. Rusa is our star student who has really shown what dedication and hard work achieves. She came here as a student from Shantiniketan with a master's from Shantiniketan, and I must say that we had a big blunder when we said that she cannot join the PhD program directly but come in as a master. Rusa stood her ground and said, no, either I come as a master or I don't come at all, as a PhD student, or I don't come at all. And she proved us wrong. She did the best in her batch, and I was very fortunate when she decided to join me for a PhD, and she did a number of papers with me and others, and some of the, I would say, hopefully classic papers, but they've certainly got her very good laurels. She went from here to Valencia as a postdoc with a very eminent Antonio Pish, and then went as a Humboldt fellow. When she got this position, she also got a Humboldt in at the same time, and then Humboldt decided they'll wait for a year for her to join at Siegen, and she remained there for 2 years and then got a group leader position which would pay her salaries. It was like €1 million. She postdocs, students and things, lot of money, and she did very, very well and made us all very proud at this institute. But she made an even more bold decision of accepting a faculty position at IIT Gandhinagar, which was offered, and they also decided they can wait for a year to get her. So, it's a great pleasure that she has decided to come here very soon after joining Gandhinagar and talk to us about indirect hints of new physics. What are they telling us? Okay, so Rusa, please.
Okay, so hello everyone, and I'm already inserted so much I'm not able to say anything from Rahul's speech. So I'm very happy to be back here to present this Diamond Jubilee colloquium, and special thanks to Shantan for inviting me here. So let's start. So as Rahul was mentioning, so I joined in 2012 in IMSc, and it was 50th birthday for IMSc, and here you can see a group photo of a conference which was organized during this occasion on high energy physics. So many people came from abroad and also within India to attend this conference, and it was like, for me, it was more or less a first experience of so-called international conference in high energy physics. So now we are celebrating 60th birthday of IMSc, and also if you see 2012 in terms of high energy physics, it's a very special year because it was the discovery year of Higgs boson. So I would like to say how things have evolved from 2012 to 2022, like this year, how the perspective from in high energy physics has changed. So of course, apart from all these people whom you see in this picture, all of them have grown older. Apart from that fact, what else have we achieved? So far we know that the Standard Model of particle physics, which actually describes the fundamental interaction between the the fundamental building blocks of the nature, and it describes so far very good. And this Higgs was the last remaining one, which was discovered 10 years ago. And after that time, so far we didn't see any direct signature of BSM particles, but we know there are some reasons why we should go beyond the standard model physics. One of the example is like from indirect astrophysical evidences, we know that the dark matters exist. Those are like 5 times more abundant than the normal ordinary matter what we see around us. We also see like the matter which are more abundant than the antimatter, and there is no reason why it should be in principle when at the beginning of the universe both of them were created at the same amount, and then why there is some asymmetry. So these two type of questions we can say it somehow has to deal with some kind of cosmological implementation of the standard model of particle physics. And then also there are certain things like we have observed the tiny neutrino masses which were predicted massless in this theory, and we have also seen this fermion mass hierarchy, like why there is a very large scale difference between the lowest fermion to the highest fermion. And these two phenomena somehow tells us some kind of ad hoc tuning of the standard model parameters, because in principle we do not predict from this theory what should be the masses of these particles. These are just some experimental facts. And also from the theoretical point of view, so all these 4 you can say these are indirect from astrophysical sources, and these are kind of direct signature from experiments. But from theoretical point of view, we know that about the problem of electroweak mass hierarchy. So basically whatever the Higgs boson mass we have observed, it's unstable under quantum correction within this theory. So if we have observed it at 125 GeV, so we somehow predict that there should be some kind of new dynamics which should be showing up at the order of 1 TeV scale to make it stable at say 125 GeV. But this is much more theoretical observation. And for these, like all these 4 cases, we do not have any clear-cut evidence or say clear-cut guess where should the new energy scale be. So, and like after the Higgs discovery, people were much more motivated to look for some popular DSM constructions which were motivated mostly from the theoretical point of view, say for example supersymmetry. But these days those are becoming much less appealing because we are not seeing anything new in the collider which were running for last 10 years after the Higgs boson discovery. So maybe somehow it's telling us that we should look for new directions. So among the 4 points, let's focus on this fermion mass hierarchy, which we do not know why it's arising like the way it is, and if there is some possibilities to connect this fermion mass hierarchy problem with the low energy data which is so far known as flavor anomalies. So mostly for the younger members in this audience, so I will try to start from the very basics, like what these 2 things are. So as I was mentioning, this fermion mass hierarchy is like if you look for the lightest fermion electron to the heaviest one top, so you see a 7 orders of magnitude difference in the masses between these 2 fermions. And in terms of the Lagrangian, when you see the gauge interaction for the standard model Lagrangian, that's same for all fermions. So it has some flavor degeneracy, and you can rotate the fermion fields, and so this U35 is the flavor symmetry which is known in the standard model for the gauge sector. But whenever we turn on this Higgs interaction, so because of this Yukawa interaction, this symmetry, this flavor symmetry is broken, and we see this very different patterns. And in terms of the standard model Yukawa sector, so this is where I just code this archetype Yukawa matrix. So here only the three element is roughly close to 1 and others are really small. So this Yukawa sector contains large number of free parameters in the standard model, and we can only experimentally just observing the particles we know what they should be. And somehow these masses and mixing angles, they do not look accidental. There might be some reason why it's like that. So these things are known as like old flavor puzzle. These are from long back. So our aim was to somehow connect this old flavor puzzle to the new one. So what are the new flavor puzzles? So these are called B anomalies. So basically in this case we have some meson, which is a bound state of a quark and antiquark. It decays to another meson and some lepton pairs. And when we construct certain ratios, so standard model predicts that this ratio should be very close to 1. And if we look in terms of Feynman diagram, so it proceeds via a loop. And what happens, like starting from 2014, LHCb has observed kind of significant deviation in this observable, say Rk, so which is lower than the prediction, which is 1 for standard model. There is some deviation. Also another mode, like the similar mode with the same quark level transition but with a k star, so we also see some kind of deviation, and both of them are the order of 2 sigma level. Also something which we have seen, like this is a differential bunching fraction for Vcb to 5 mu, another decay channel, and in this case you see the theory predictions are these bands and the experimental data is this black error bar, and in this case we also see something is not matching. This is also a deviation in the level of 3 sigma. Some other tensions or discrepancies are also observed. So in charge current B decays, so this is again we construct some ratios with different flavors of leptons, and this is a tree level transition, so B to C via tree level W. The previous one was a loop level in the standard model, and in this case you see various experiments, LHCb, Bawal and Bell, they have entered into the game, and this red blob is the current experimental average, which is differing from the standard model prediction, which is this small black error bar. So combined deviation is at the level of 3 sigma. And also at the same type of quark level transition, we also see a discrepancy where the data is always saying like it's larger than the standard model prediction. This is where we change the final state mesons. Those are in the quark flavor sector, and you might have also heard about this anomalous measurement of muon magnetic moment. So very last year, I think no, last year, Fermilab has confirmed the BNL data of this muon G-2 measurement, and in this case, so you see this deviation from the theory prediction, but even in the theory prediction there are certain things which are somehow not very clearly known how to evaluate. For example, this G-2 observable gets correction from QED, also from electroweak, which are under control, but some diagrams or some contribution, this hadronic vacuum polarization, which are difficult to control, but there are certain deviations if we observe from the data driven approach to the Fermilab data. So probably these are the very important deviations which we are seeing in particle physics in the last say 7-8 years after the discovery, and then we are trying to say what can be the possible reason for this. And this whole topic, what I was saying you, the flavor symmetry and dealing with all different flavors of quarks and leptons, so we can call it flavor physics. And let's if we assume that the flavor physics is some ship, so basically I just borrowed this slide from Thomas Manel. So if we call flavor physics is a ship, so then there is a fun deck where people do the new physics model building. So we treat all these tensions or these anomalies very seriously, and we say like, okay, these are some deviation, so let us modify the standard model of particle physics and do some kind of model building. That's the fun deck part. So let me first go into the fun deck part and how we work there. So first thing, if you notice, all these B meson decays or say muon G minus 2, these are low energy processes compared to the direct searches at LHC. So one easy way to go with the EFT approach, effective theory approach. So for 4 fermions operators in dimension 6, which are constructed from say standard model fields and symmetry, so there are like 59 operators if you assume them flavor universal. But then if you expand them in flavor non-universal direction, so this number is huge, 2500. So then if you ask that, okay, with 2500 operators, let us try to observe what is happening, how do we fit or how do we explain all these anomalies which I was showing. So it's kind of hopeless situation to find any non-zero effects in this huge parameter space. So one way would be if we can select a subset based on the symmetry assumption that I will be coming. So physicists always try to simplify problems with assuming some kind of underlying symmetry of the theory. Or another way is like treat each anomalies or the hints or the tensions independently. It might be that all of them are not somehow correlated. And why I say so, that why they are not correlated. So let's just take one example of an EFT operator. So this is a 4 fermion operator, and this C is the Wilson coefficient. So if we assume there is no assumption on C, so C is say order 1 value, then for RK star, which is a loop level process, to explain the deviation what we are seeing at the at LHCb, we need a new physics to show up somewhere around 30 TeV. Similar thing we can do for RD star, that's a tree level process. So to get that huge enhancement, we can say that we get that with C equal to 1, the new physics scale should be around 3 TeV. But there is no way to understand why this assumption should be true. For example, if we assume like minimal flavor violation, for example, the flavor symmetry which is broken, which is only by the source is only from the standard model interaction, the Higgs interaction, the Yukawa interaction which I was showing. So if we assume that, then this goes as the CKM, and you can lower the scale to 6 TeV from say 30 TeV. You can do further manipulation. So you can say, okay, my new physics operators are arising at loop level and it's also obeying MFV. Then you can further lower it to like 1.5 TeV. So in principle, this new physics scale can be lowered or can be changed depending upon what's happening in the flavor dynamics. So the flavor structure of the theory is very important to understand, where we are actually expecting the new physics from these tensions or the hints. Even similar thing can be done for muon G minus 2. It has some different sets of operators, and in the standard model EFT we can even allow like the new physics scale to be 100 TeV, which is probably far beyond the reach of the collider, even for the future colliders which are proposed. So then how do we proceed from here? So since flavor dynamics is so important, so one way is to go like we go for simplified models. That means we look for certain motivated or say popular BSM setups, BSM models which can contribute to this type of channels, this type of tensions. For example, the B2S is RK star. You can have these sets of models, D prime, extra dimension, leptoquarks. For B2C, we can have 2 HDMs, W prime models, or say leptoquarks. And these leptoquarks are common in both the places. So what are those? So this is some hypothetical scalar particle which can turn, not scalar, okay, scalar or vector, which can turn a lepton into a quark. And here you see like from the standard model gauge symmetry we can actually write 10 of them. So 5 of them are scalar and 5 of them are vector. And this is, leptoquarks are not at all any new idea. So if you just do a search in Inspire HEP, you will find more than 2000 papers which deal with the word leptoquark somewhere in the text or the reference somewhere. And this word was introduced by Nelson and Greenberg, but the concept of this lepton-hadron unification was proposed by Pati and Salam in 73. So then the question is, if it is there from such a long time, then what makes it interesting after this almost 50 years? And the answers I have already given you in the previous slide. So these B anomalies, or say you can say the peculiar nature of the B anomalies, which made people to go back and look for some of these BSM scenarios which were not appealing at that moment. So then the question is, how do we determine this new Yukawa structure? As I said, the leptoquarks couple to a lepton and a quark, so this coupling is again unknown for us. So one technique is we fit two data with the brute force method. So again we end up with getting large number of free parameters. So the second part will be like we deal with some underlying symmetry of the UV model, which not only reduce the parameters but will also like give us some reasonable conclusion. So as I was already mentioning, this minimal flavor violation, so flavor interactions which are involved linked to only the standard model Yukawa structure. So we can actually make these Yukawa couplings of the leptoquarks as flavor spurions. So basically there are some auxiliary fields which were generated by breaking an extra symmetry, say U1, which we called Fogart-Nielsen symmetry, and we also include the charges for all standard model fermions in this setup. So what's the advantage of doing this way? So again I am back to this 4 fermion operator. For a generic EFT, there are like 4 indices, so we have like 81 parameters if we don't have any assumption. For MFB, which I was saying, we can reduce it to 6 because these are only linked to the standard model Yukawa structure if we don't assume any new source of flavor violation from the leptonic part. And when we do the Fogart-Nielsen, so basically these Wilson coefficients, they actually go as some power of the small expansion parameter of the U1 breaking term, which I am calling here the lambda. And these are like different charges, generation dependent charges for all standard model fermions. But again, it doesn't help in that sense. We have large number of freedom. So, but in the case of Fogart-Nielsen with leptoquarks, we can factorize things into 2 parts, and the expression is given here. So basically we reduce the system into like something around 20 new parameters to deal with. So with this framework we try to introduce 2 leptoquarks. So I have shown you the table with 10 leptoquarks. Among those we take like S3 and S1, and we write the interaction with the standard model quarks and the quark doublets and the fermion doublets, which is shown here. And this SQL, these are the spurions which goes like this. Now in this setup, the nice thing is that these spurions or these structures, they are not at all independent, or we don't have any freedom, because we need to provide the correct masses for the quarks and the leptons which are already observed at the experiments. So these charges are fixed via these masses and the secant angle, and the lepton charges we need some processes to compute. So for example, there are various different processes. These are 3 channels, so B2 C tau nu, B2 SLL, where we want some kind of enhancement because we are seeing anomalies here. These are some channels which we want to be within the limit which are observed. And there are also loop-induced processes. And with this setup, we are able to explain this, the discrepancies RK, RK star, or say RD, RD star, and also we can explain why this fermions in the Standard Model, they have such a peculiar, or say very wide gap between the mass scales. So we can give a dynamical reason to this difference, or say fermion mass hierarchy. And not just that, so there is some predictability of these models also, because we see enhancements in modes which are where we have muon and the tau leptons in the final state. So here I have quoted some modes where you see the Standard Model predictions are either 0 or say even very small. This third column is the experimental current limit, and we have quite significant enhancement, say for B sub s to mu tau, which is just 1 order below the current limit, even in this case for B to K mu tau. So basically the claim is like, if we are really seeing some kind of evidence of say these hypothetical particles via these anomalies, then we should see something in these other decay modes, and any improvement of this measurement, say from LHC-B or say from Bell, will be very important to identify this combined explanation for neutral current and charge current anomalies. So that was something we tried for the combined explanation. Then other thing was what experimental inputs we actually need to better understand, say even individual cases, because I was already motivating you. In principle, there is no reason to believe that all these different tensions or the hints should be correlated, and it can be possible that individual cases are different. So to do that, we had some closer look on B to C tau nu. So basically, so here we are seeing some deviation in RD star, and there are also measurements of longitudinal polarization fraction and D star. So if you see, there are various mediators in terms of simplified models. Some of them are scalar vector, or this which is quoted here, and they give rise to different set of operators. And when we try to explain the current deviation, we get some better compatibility with say one particle, but even in terms of numbers, these are really close, and we cannot correctly exclude which is there in principle, or which is the most prominent candidate to explain such a tension. So then it is very crucial to perform this full angular analysis. So angular analysis are known for long back. So basically, when a B meson decays to some other hadron, which can further decay to two states, so you have a 4 particle final state here, and they can go in different directions. So you can construct the angular observers which are measurable at say LHC or say at B factories. And we have shown that in some of these angular observers, say B and say I1C and IS, it's possible to distinguish different new physics signatures which were not possible just by looking at the fit results for the tensions. So from experimental point of view, we really want these measurements of say angular observables to identify which type of new physics mediators are involved in such a channel. Then from experimental side, there is some interesting involvement which is going on for this particular mode, which is B to K nu bar. So if you compare this mode with its counterpart, which is B to K or say K star and charge leptons, so theoretically this neutrino mode is much more cleaner than the charge lepton, because we don't expect any charm loop effects in those cases, because these are neutrinos. But experimentally, these decay modes are very, very challenging, because we have 2 missing neutrinos so far, and no signal has been observed. But very recently, Bell 2 has come up with an intrusive tagging technique. So basically, when they collide when they have this upsilon 4s decaying to the 2B mesons, so one side they used to have the semi-leptonic tagging or hadronic tagging, that means they are fully constructing this side, but now they have changed the technique so that they can balance the different decay kinematics and parameters for both the sides, for the signal side and the tag side, and that's what they somehow got higher efficiency. And the current situation is this very preliminary data from Bell 2, which is shown in this red bar. At the moment it has quite large uncertainty, but it's expected to improve, and the currently observed the expectation is actually currently expected events are larger than what was predicted, so this gives some kind of average which is shown here, and if you take the standard model value, this is saying it should be roughly 2 times. So we try to correlate this signal with the B anomalies which we have already observed at experiments. So here are certain summary plots which we have done in this work, and Rahul is also involved in this work. So basically, if you see, if we try to explain, say this is charge current, so RD star, so it's possible, for example, this S1 leptoquark can generate such a 2 times enhancement for RK and RK star nu in this combined setup. And if we try to relate with neutral current anomalies, so then the anomalies can be explained very nicely, but we do not see any enhancement for RK nu, I mean any enhancement in this neutrino channel. And in combined setups, it's possible that this S3 leptoquark and another U3 vector leptoquark can show this desired enhancement. So again, any measurement on this channel will be very important to confirm or say even falsify various BSNL setups. So that was some kind of fun deck part. You know the tensions, so you have operators, so either you play with the operators or you have some simplified models to work out and try to see if those tensions can be observed. And then the next comes this in the flavor ship, so there is also a machine room, that means how this ship is going, so you need some kind of work to do the hadronic computation, because whatever I was mentioning, all this involves hadronic physics, so meson transitions or say even in some cases baryon transitions are also there. So let me come to that part. What are the interesting things going on in this hadronic computation regime? So there is also another puzzle which is known as this Vcb puzzle. So Vcb is a CKM matrix element in the standard model, and when we compare its determination from say exclusive and the inclusive measurements, so there is some tension. So this is currently the H-flav average for all the exclusive channels, and the inclusive measurement is the black error bar, and you see these two are not at all matching even for VCB and also a bit for VUB. But I didn't put this puzzle into the first part of the talk. There is some good reason, because the observables which we are looking at in the first part of the talk, they are in some sense clean from the theoretical uncertainty. That means clean means they are constructed as a ratio, so somehow this unknown hadronic physics were cancelling, so we were very sure in some sense that the theory is very kosher. So if something is wrong, probably is from the experimental side, or I mean at least the assurance from the theory side was much more strong compared to these things. Why? Is such because when we measure say this VCB from exclusive determination, we need the form factors for all these decay modes. So for example, this green bar is obtained for B to D and B to D star and B sub S to D sub S channel. So in all these cases form factors are needed, and we need non-perturbative methods to compute say light cone sum rule or say lattice. And there are several results from lattice groups, so one has to compare actually from which one they are using. So just motivated from that puzzle, we tried to look for some excited charmed mesons. So here you see a table. Those are like D and D star were there in the previous slide, but there can be D1 and D2, and here are this spin and the parity of these mesons. And these excited mesons, they also provide complementary information, because if we measure them at the experiment, it will give rise to new extraction of Vcb. So then if I go back, then we will have, say, another band somewhere for this Vcb prediction from these new channels. And secondly, not just Vcb, they are also important in understanding the backgrounds of RD star, these anomalies which I was showing, this B to D and D star decay mode. And also they are important to identify the extraction of VUV, because even if the U quark is not involved, so for VUV extraction one has to separate out in the phase space about all these charmed, properly one has to separate out all these excited charmed meson backgrounds from the measurement. And another interesting thing we observe, like if we look at PDG and we see the exclusive channel prediction branching fraction, so there is a 25% gap between the sum of all this exclusive channel with the inclusive one, where the exclusive channels are dominated. So how much we can fill this gap, that means this excited mesons or say continuum are somehow contributing more in this inclusive modes. So far there was no estimate for the form factors available in the finite C quark limit, so only in the HQET limit there are some predictions. And also something is critical here, because this D1 and D1 prime, they are very close in mass. So if you look at this, just a 10 MeV gap, and one of them is quite huge, like this large width. The width is very large for D1 prime. So we use this method, this non-perturbative method, to compute these form factors, which is called Qcd Sum Rule. So it's basically based on operator product expansion, and where we separate it in two parts. One part is perturbatively calculable amplitudes, and another part which describes how this Qcd vacuum characterized. So basically the quark and gluon condensates come, and then we use the dispersion relation to relate these to physical hadronic parameters. Of course, here you can see there are many assumptions are going on into these methods, but in some cases these are the only methods to deal with, and there is no other option. So because non-perturbative physics is always difficult. So the limitations are, we really have to assume some model answers for the hadronic spectrum. So for example, this assumption here is this spectral density is mostly dominated by the ground state, and then we are separate the things in the continuum. And in our case the situation is much more complicated. The reason is, it's not just only one ground state, we have two ground states here. So if I go back to the previous slide, so as I was mentioning, we were trying to evaluate the form factors for say D1 and D1 prime, which are very close, so, and also large width. So this also complicates the situation. So what we did, we started with the correlation function of two independent currents. So here you see the two dimension 4 currents, J1 and J2, and this part of the correlation function, which is proportional to the metric tensor, it interpolates both the 1 plus state. And for the hadronic representation, we actually convoluted with the Bright-Wigner form for this large D1 width. And then we perform the matching of the OP with the perturbative part and the condensate part. And as a result, so we end up getting 3 Qcd sum rules, like we have two currents, but with 4 decay constants, because two currents, both of them are convoluted in two mesons, so at the end we have 4 decay constants. So kind of underdetermined systems, we cannot solve it without any external input. So in this case probably branching fraction is something which can help us in evaluating this system. So here are these results for the form factors. For these are all 4 form factors for B to D1, and there is also this twofold ambiguity because of this quadratic dependency on the form on the correlation function, and we also see kind of large uncertainty. So in that sense, these results may not be that great at the moment unless we get some kind of lattice inputs from on say any of the decay constants, which will help us to reduce the uncertainty or even to choose which ambiguity is actually present. But however, if we look for the ratios, so again the ratios are something cleaner, which I was even mentioning in the beginning of the talk. So in that case we really find this large uncertainties cancel, and we can predict the analogous to RD star what will be RD1 and say RD1 prime, and they are actually same and with very small uncertainty. And there is also something interesting going on in the non-leptonic channel, which needs much more attention. So for example, this is decay of B sub s to D sub s and the pi mode. So this is a color allowed 3-level decay, and in this case it's proceeded via this W exchange, and you see the 4 different flavors of quarks in the final stage. So these channels, this B sub s to D sub s pi and or say B sub s to D plus and K minus, in this case we don't have any annihilation or say any penguin contribution. But again you can notice so far I was dealing with decay modes where at least leptons are present. So those are semi-leptonic channels, that means the B meson is decaying to one daughter meson, but there are leptons, so it's easier to control the QCD effects. But in this case, even in the final state we have hadron, so it's a fully hadronic decay, and we do not have very good understanding what's going on, but the theory predictions only rely on QCD factorization. And when these branching fractions are actually compared with the very latest preliminary data from Bell 2, so there is a very a huge deviation of almost on the order of, I don't know, even greater than 5 sigma level with this Bell 2 result. So it somehow tells us like we need to either modify or something is wrong going on either in the QCD factorization estimates or maybe in the experiment setup. So there are of course works where funded people, you can say, so doing some kind of new physics model building. So in terms of say W prime models, so those are like favorites which can explain these anomalies, or not anomalies, how do I say, these are some deviations, preliminary deviation or say puzzles. And yes, so W prime is one of the favorite, and but one also can also relate it to the constants from direct searches, say from the LHC, the 2Z searches, because whatever the new physics models you involve here, it will give rise to it will decay to the light quarks, and there is very strong bound from LHC because so far they didn't see anything, any excess in this channel. So the new physics part is very, very constraining for these decay channels. And so for the theory estimates, there are quite some works here. So people try to evaluate the higher order corrections for this, even for the power corrections. People even use the light cone sum rule methods to compute the soft gluon exchange in these modes. So far they also do not see any huge contribution or say huge correction required in QCD factorization, but of course we need much more effort to understand what's actually going in these two modes. So this is also some channels which are interesting these days to study from the hadronic physics side. So yes, so I think I come to the summary slide. So basically, when from the very beginning I was saying like this neutral current anomalies are there, charge current, there is muon magnetic moment. It might be possible that they are correlated or they are not at all correlated, and might be even possible that some of them just vanish. Even there can be some experimental drawbacks. Some of the observers which we know that from theory point of view are very clean, but experimentally something wrong might be gone there, so we do not know. And one possibility is that we can actually correlate and try to see what kind of signatures of new physics we are getting, because at the moment, since we are not directly seeing any new particle at the collider, so these are the only few things with which we can go forward and try to speculate about the possible DSM scenarios. And also we need a lot to understand what's actually going on from the hadronic physics side. So I gave some example on this Vcb puzzle. We need to know this charmed mesons and also how to actually deal with Qcd factorization, which is there for quite a long time, and for all other channels it's matching, but suddenly for two channels these predictions are not matching. That's also interesting to look for. And with this, so we definitely will have some answers on these modes, because LHCb will be running for 10 years and as so for Bell 2. So we are here somewhere here in this 2022, and we will collect huge amount of data in these two experiments. So there will of course be some kind of validation of discrepancies observed so far. So either we get confirmation, or even it's possible that we get some kind of new signatures from these machines. And also there are plenty of channels for B and C hadron decay channels which are yet to be explored, because many channels where we do not have at all any theory predictions. So even if we have some data from experiment, we do not know from where to, with what prediction we should compare it. So it's in that sense kind of very exciting time for flavor physics, because these will be there for, these machines will be running for 10 years and we have plenty of new things which will be coming and going. So thank you very much for your attention.
Thanks, Rusa, for this very comprehensive talk. So it's time for questions.
So I have a couple of questions. So my first question is in standard model we have 5 flavor fields. So on which basis we kind of decide that? We have quark left field and doublet, and then UR singlet, and then electron singlet, and that's how we have 5 kind of flavor field. So I don't know how, on which basis we decide that to kind of to write this in this exact manner, like in this manner.
In the manner how it is written in standard model, you mean?
Yeah.
So okay, that goes back to the question in 1960s, how they started writing, right? So you mean how you divide into something into SU2 or in something in in U1. So these what I mean by flavor physics, that's actually not how you divide into, somehow it's not going. So the flavor physics is like you have 3 identical replica of particles, and then they are separated into masses, like a huge mass gap So I think if you, I mean, I don't know exactly where you are pointing, but I think if you want to know how this theory is written, but it's something which worked out for this grouping the quarks and the leptons in this manner. Even if you see, people didn't know whether there will be like 3 generations of quarks. There was no such a indication. So people started even with 2 generations. And then somewhere this flavor physics came into part. There were certain channels in kaons where people observed something and then they didn't know how to explain it, like k belong to mu plus mu minus, right? So then they did not know how to explain this data. So then they came up like, okay, maybe it's possible that some new particles going into the loop. That time it was not known, now it's the charm work. So it's like experiment which guided us to group these particles in this way, but also from the theoretical point of view, people started with say 1 generation and then made this replica from the experimental side.
So like in your initial slides you said there is a Higgs mass instability. So actually I like in a standard model we say that fermions have stable mass. So don't we get contribution like we have some tree level mass for the fermions and we can get masses from the loops also. So why are we are not considering that one? In this way then there will be instability in fermion mass also, right?
So it is protected by some symmetry for fermions, but for scalar you cannot give any reason to protect its mass. So for fermion you cannot increase its mass to anything else because it's the Standard Model symmetry which is not allowing it to increase. But for scalar, whatever the way Standard Model is written, you cannot have any guarantee like this mass should be there. So that's why this only the one scalar particle is there, and that's why it is so special.
Okay. And when we write 3 generation, like we have relation, that's how we decide n minus 1 number of phases, n minus 1 multiplied by n minus 2 divided by 2. So that's how we decided there will be 3rd generation, like Kobayashi Masakawa matrix. That's how it came into the picture. So why don't we try for looking 4th generation? Is it mathematical difficulty or experimental problem like so?
No, mathematically you can enlarge the group and you can easily include 4th generation, and there are many works which were going on 4th generation, but then experimentally it is becoming less appealing because we are not able to see those things. So in principle you are correct, you can easily write and extend it, but then you have to be consistent with experiment, and it's not yet so far found.
Thank you, sir.
Okay.
Yeah.
That's one of the things.
Yeah.
And also what happens is that experimental search for 4th generation is sort of putting limits which are quite unreasonable. You know, there are corrections that will come, and so it becomes more and more difficult, not appealing as you said. Yeah. But neutrinos automatically, like neutrinos, it won't be possible because that invisible width is measured. Yes,
Yeah.
but generations will be okay.
It's a theoretical thing.
Correct.
We know SM is anomaly free.
Yes.
So if you have to extend it, then you have to make sure that it remains so.
New
Yeah,
gauge is
but
anomaly.
each
Otherwise
generation,
consistency will be gone.
So each generation you can make anomaly free. That's correct. Yeah. Okay. It's all right.
I have one question and one comment. The question is this, that I saw increase in luminosities over the next decade or so. So where is the likelihood of seeing new physics among all the anomalies that you discussed?
This is a very difficult question, right? So
Just as information.
yeah, I don't know, but if this flavor anomalies really stay, so then we should see something at the order of 10 TeVs. Because as I was showing you in terms of these scales, so each of them come with different new physics scale, like here, right? So just from looking from EFT perspective it is difficult, but at least from these numbers people should expect something to be at the order of 10 TeVs. But even if some of these anomalies are gone, then you can forget about that reason, right?
Yeah, because anyway we know that standard model is not complete.
Yes.
I mean neutrino mass is staring at us, oscillation phenomena is staring at us, and all those things are not in the usual standard model where neutrino is massless.
Yes.
So the physics beyond standard model is already staring at us. So the question is to look at the most likely places in every sector where we can catch it.
Yes.
And I think that's what you are saying here.
Yes.
That was
So in slide 18 or 19 probably you have RHN. Is that a right-handed neutrino?
Let me see. Yeah, might be there. I didn't.
The last one, the one with the red pink plots. Yeah, so you,
Yeah, I didn't mention it. Yeah, that's true. So actually what we did in this model, I just skipped all the details. So here we even, so this was which channel? Okay, if I go back, this is slow.
No, so my question is,
Yeah.
is essentially like what kind of right-handed neutrino models are being considered at all in flavor physics, if you have worked on it?
Yes, so the so you can have this. I mean, for right-handed models, you have this seesaw mechanism, right? So, in principle, what our aim was like, say it's B to D L nu. So, this neutrino is missing. So, why not? It is a right-handed neutrino, the low mass right-handed neutrino. So, there are different models. So, depends on how you make the seesaw. So, the seesaw is the popular framework. Even the inverse seesaw is also like, I mean, type 1 and type 2, type 3, there are so many things. And also you can say it is not even a right-handed neutrino, you can say it's some standard model gauge singlet fermion, and you can even call it as a dark matter candidate. So then you can have some Z prime models. So there are many possibilities, W prime models, but the framework, mostly right-handed neutrinos were introduced to give the masses for light neutrinos, like to give a reason why these light neutrinos have tiny masses, and for that we need these different variations of seesaw.
So, but here the right-handed neutrino in those models are GeV scale, like they are very heavy. Yeah.
In this case, we dealt with the EFT approach, so these are very light.
Okay.
So you can call it sterile neutrino. Generally, right-handed neutrino people use for the masses are TeV range, and sterile if it's low mass.
Okay.
Yeah.
So, I mean, is there any possibility of connecting this with the neutrino anomalies, oscillation anomalies?
It's possible you can actually cook some model where it's also contributing, but yeah, what we considered, we didn't look. We just did the EFT approach, and we didn't even had the full concrete model like the UV model. For us, this was just some operators to see the effect, but yeah, you can always connect those.
Okay, thank you.
Hi. So, my question. So, I could not understand why it is a hierarchy to have fermions have very low mass and very high mass.
This term hierarchy in this case is used like, I mean, why there should be these 7 orders of magnitude. I mean, is there any reason, or it is just a completely some experimental phenomena? So in that sense, this term hierarchy is used, but this is, if I go back, so just some free parameters in the standard model, and we fit, okay, we found electron masses here, we find the top masses somewhere, and we just fit the data. So is it just only that much, or we really have some kind of dynamical reason to say like, no, I have this neutrino masses, which in our case for the model particular which I have shown, so in that case this the electron masses, they are depending on some powers of the extra symmetry which we have introduced in the theory. So it gives some kind of dynamical reason why the masses are so small for electron, or say why the mass is so large for tau.
So yeah.
Huh? Then it's even worse, right? Yeah, huge difference.
So when you have a reason for why this is happening, then why do you call it a hierarchy?
Then we don't call it hierarchy.
Okay.
So in the standard model we can call it hierarchy, we don't have the reason. But when I just gave one example of this Fogart-Nielsen model, there we don't call it hierarchy at all. There we have the dynamical reason. Yeah.
Okay. Thank you.
Any further questions? Okay, let me ask one question. So in the end you mentioned that it is possible to get some clues about the beyond standard model from flavor anomalies as well as mu on G minus 2. In the mu on G minus 2, the lepton sector is very well understood, the contributions from the lepton sector, right? So
no, I mean mu on G minus 2 we also do not know how to explain, right? So,
but it is mainly the uncertainty comes from the hadronic sector.
Yes. So that's what I mentioned, like if we think that the data driven approach is giving us the correct estimate for hadronic vacuum polarization, then we have deviation. If we believe in lattice results, right? So of course that observable is not in that sense as clean, but let's see how it goes. So in principle, because even if we say that hadronic vacuum polarization is matching with lattice, and then we have to say the data driven approach, that means E plus E minus collision, all these are quite wrong, so all these are quite off. Then we also have to give reason why they are off, and also those are completely matching with electroweak precision sector, all the electroweak precision data. So then we are also traveling that side, but maybe it's possible that we find some middle ground for hadronic vacuum polarization where it is consistent with electroweak precision data for this data driven approach, and also lattice is in between, and it's more or less 1 or 2 sigma with mu on G minus 2. So then everybody is happy, but otherwise we still have this discrepancy. Yeah.
Okay, I see no further questions. So thanks again, Rusa, for coming and giving this wonderful talk.